All right, so it is time for us to make another transition. We're going to move from the effects on planets and the physical causes of space weather to the how do we observe it question. And this is going to come in two phases with our last two talks. The first one looking inward at the solar system and a few key ways we can observe space weather there, what we've learned, as well as a few spots, I believe, where space weather is still somewhat hidden from us. And then we'll look outward for the last talk. So, our instructor for this lesson has been conducting cutting-edge research in solar space weather for the last 25 years right here at Caltech's own Space Radiation Laboratory. Her specialty is the energetic particles that are emitted by the sun, both in steady streams and stormy bursts. And she has shaped the course of this field through her career as a result of a ton of service and leadership. An example of this, one of many examples, is serving as principal investigator for two separate instruments aboard the Advanced Composition Explorer, ACE, which is now well into its third decade of observing solar space weather in situ. So it's hard to imagine someone better qualified to teach us about this than a dean of the Heliophysics Summer School, Dr. Christina Cohen.
All right, so this is the view from the inside. So I just want to press upon you that we have a lot of measurements, right? So this is the NASA's Heliophysics System Observatory. These are the spacecraft that NASA basically runs. Some of them are joint with JAXA or ESA and various different things. But you can see there's basically 19 missions here that are currently running. That's about 26 spacecraft, because some of those missions are multi-spacecraft. There's something like 13 that they're developing, one that they're studying, and that's just currently. Going forward, there's going to be a lot more. So there's lots and lots of spacecraft that are, a lot of these, of course, are observing the Earth, but a lot of them are looking at the sun and looking at material that's coming from the sun and its impact on Earth. So we have a lot of measurements that we can utilize. And in addition to these science missions, NOAA has its own observatory system, which of course focuses on weather, you know, the kind of weather we worry about here, whether it's going to rain or snow and stuff like that. But also they have spacecraft that are what they call deep space. For them, deep space means L1, so it's like 1% of the way to the sun. But anyway, they have a couple of spacecraft. There's Discover there. SWIFO is going up hopefully in 2025. And they're measuring, their thing is that they have to measure 24/7, 365. Nothing can fail. It's always got to work kind of thing, because they've got to make predictions of space weather and how it's going to impact the various spacecraft. Unfortunately, I'm not going to be able to talk a lot about that. That's a whole nother lecture. But we can actually use some of the measurements from these spacecraft for our science data as well. And in particular, I want to point out, I'm getting a feedback, so sorry. GOES here, GOES spacecraft that are in geosynchronous orbit. We use a lot of data from them because they measure protons really well over a wide range of energies. Okay, so this is the kind of things that we can kind of group these observations into what we call remote sensing and in situ observations. And I'm going to start with remote sensing. And what you're going to see here is imagery from a bunch of different spacecraft. This one's from GOES that I just mentioned. This is the SUVI instrument, which measures ultraviolet, and you can see features like this dark area here, which is a really nice coronal hole. So you can see coronal holes when they go around the sun. My favorite version of this is this guy, who I often use as my background when I'm feeling happy. This is the kind of thing that you've seen before a couple of times. These are coronal mass ejections. This is a couple of different coronagraphs on the SOHO spacecraft. LASCO, which has also been up as long as ACE. It's been up there for many decades, but you can see these beautiful coronal mass ejections and then the energetic particles that hit the detector and create the snow. This is Solar Dynamics Observatory, which is looking, actually, this is a composite of a couple of different wavelengths. They do all these different wavelengths. You can see that nice flare go off. Sometimes you can see this coronal dimming, which I think Julie's going to mention later. Excuse me. And then you can look at the different layers of the sun, basically, from down in at the photosphere all the way up into the corona and see the different features and how they evolve. We can use these chronographs, we can also process these and just see the outflowing of material. This is the solar wind, and you can see that despite the statements of quiet solar wind, even in quiet time periods, it's not very quiet. You can see all these structures coming out, this striations that are going on here having to do with streamers and areas of coronal holes. You get plumes, all kinds of stuff going on. And then, of course, the coronal mass ejections. This is just a snapshot here where you can see the different structures. So you can see the driver of the coronal mass ejection, and you can very faintly see ahead of it is the shock. This one's actually coming towards you, so it's sort of filling up your entire view. Sometimes we see ones going off the side, and you can see the structure even more. But these shocks, as was mentioned before, these can accelerate particles, so that's something that we're very interested in. The flares as well can accelerate particles. And we can also see these shocks in other remote sensing, including radio data. So what we're looking at here is frequency as a function of time. These are electrons that are emitting radio. The two different features that are labeled here are type 2 radio bursts, which have sort of a slower drift, meaning how fast they drop. How fast they change in frequency as a function of time is a little slower than what type 3 is. Basically, what you're tracing out here is that shock as it's moving away from the sun, and it's accelerating electrons, and they're emitting as they go along. These type 3 radio bursts are actually tracing open field lines. These are field lines that are already open, connecting to the sun out into our heliosphere, and the electrons are just zipping down those lines. So you can see that they emit and change frequency very, very quickly. But whenever we see a type 3 radio burst, we know that there's open field lines going on there. And so we know that there is access for charged particles to come out. And when we see the type 2 radio burst, we know that there's a pretty decent shock that's being pushed out by that, or usually created by that coronal mass ejection. Okay, so here are the in situ observations, and of which we have a lot. So let's just start with solar wind parameters. So I'm not going to try and go through all these different things here, but basically they're all as a function of time. This is the magnetic field. You can see it varies. These lines that are drawn here are identified interplanetary shocks. You can see that the magnetic field goes up during those time periods. These are two different calculations of angles for the magnetic field using different components of magnetic field. And one thing that is often a nice signature is if you're in that coronal mass ejection, if it passes over the spacecraft, sometimes referred to it as an interplanetary coronal mass ejection. But when that coronal mass ejection passes over, you often see these rotations in one of those angles, and that's indicating that you're going into a helical structure that is rotating around. And then, of course, we have the solar wind. This is the radial component. You can see it goes up during these shocks as well, and the density and the temperature and a bunch of other stuff. And so through all this stuff, you can identify all these different types of solar wind. You can identify the shocks, you can identify the passage of the CMEs, you can identify the coronal hole wind. As Julian mentioned, those all have different parameters that you can, different characteristics in the solar wind that you can measure. Another one that you can measure is charge states of the solar wind. These are charge states of heavy ions. So you can look at the oxygen +7 over the oxygen +6. And the more oxygen +7 you have, the hotter the material is, and that often comes with a coronal mass ejection as it goes by. Same thing with the average charge state of iron. If it goes up, you're looking at hotter plasma that's come from a hotter place in the sun. So my favorite, of course, is solar energetic particles, which I'm going to spend most of the rest of my time on, just to give you an idea of how these fit into the scale of solar wind. You're looking at oxygen intensities. This is summed over years. And basically, as a function of energy, the solar wind is up here, right? So there's a lot of solar wind in comparison. These are particles per centimeter squared. It's an intensity. But and the slow solar wind is usually around here, which is equivalent to about 400 kilometers per second or so. You get a secondary bump because sometimes that solar wind is faster. So when you average over the whole thing, you get sort of another bump. If you go way down on this tail, you get to this sort of section, and that's where the solar energetic particle events live. And you can get a bunch of them. They all kind of add up to give you sort of this nice smooth curve. And then if you go to the very highest energy, you're talking about galactic cosmic rays. But you can see that there's many, many, many orders of magnitude going on here. And so the difficulty is if you want to measure this entire distribution, you can't do it with one instrument. You've got to put a whole bunch of instruments. If you're lucky, they're all in the same spacecraft. Then if you're really lucky, you get to intercalibrate them so that they actually give you a consistent picture. And that's what we try to do. This is data from ACE. But we try and do that. Sometimes you have to do it through different spacecraft. Sometimes you can do it all on one. So energetic particles, we measure their intensities. This is a series of events. This was actually already mentioned. This is the October, what we call the Halloween storm event. It was actually not just one event, it was a series of events. You can see, depending on how you want to count it, at least 5 events here going from October 26th to about November 10th in 2003. This is intensity at a bunch of different energies going from about 0.1 MeV per nucleon to about 50 MeV per nucleon. And these are the X-ray flares, X-class flares that went off during this time period. And you can see there was many of them, and some of them very big, X28. This is a logarithmic scale, of course, for this X-rays. And the lines that are drawn here are the shocks that were observed in the solar wind. So you can see there's a very, very busy time period, lots of stuff going on. And the interesting thing is that the intensities of the ions and also the electrons, but in this case we're just talking about oxygen, their response to this kind of activity really matters what energy you're looking at. So you get events such as this one where at the highest energy here it's pretty high compared to, say, this event, which was much lower. But at these lowest energies, it's peaking when the shock actually comes to you. And so it has a very different time profile of this red curve compared to this sort of brownish curve that's down here. And that, even in the sequence of events, you get very big events and slightly smaller events. The spacing of the different curves there tell you basically how hard or soft the spectrum is, and that also changes as a function of time. And we can integrate over those and get that spectral shape. So if you look at protons, this is an integral and fluence spectrum. So basically, you've got the number of protons with energy greater than some energy as a function of energy. This is this one right here, this blue curve, is one of those events that was just mentioned. But here are some historically other very big events. And you can see that they vary dramatically in terms of their shape of that spectra. Sometimes they're really high at low energies. Sometimes they're very high at highest energies and less so. So their hardness also changes a lot. We can do this not only for protons, but we can do it for protons, helium, all the way through iron. So we can do it for a lot of different elements. And you can see sometimes their shapes are very similar. Sometimes they're not quite so similar. One thing that's kind of interesting is they all seem to be kind of parallel here, but you'll see the energy at which they roll off, what we often call the break energy, differs as a function of the element. And we think that's signatures in terms of what the turbulence is, the strength of the shock, the conditions in which the acceleration is happening for all these different particles, because they all have different rigidities. And so we'll get back to that in a minute. But from this, of course, we can calculate the composition. So you can now take it, either integrate over energy or take a given energy, and you can compare how much iron you have to, say, oxygen. And that's the kind of thing you get here. So this is, each one of these dots is an actual SEP event. You've got the iron to oxygen ratio integrated from, in this case, 12 to 33 MeV per nucleon. This axis is just the silicon fluence, so you can just think of this as a measure of how big an event this was. And you can see that the composition here varies by orders of magnitude. So they're very different from event to event. They're also very different in size, as you can see, which is not surprising. The other thing we can do is we can look at isotopes. Not all instruments can do this. ACE was really great at this. We could do helium isotopes in particular, helium-3 to 4. That's a nice thing that we like to look at because helium-3 is very, very rare in this sort of generic solar wind. So if you're accelerating, if you have a shock going through solar wind and it's accelerating particles to higher energies, there shouldn't be a lot of helium-3 in there. What helium-3 does get accelerated in is through resonant heating in flare acceleration processes. So if you see significant amounts of helium-3, like the solar wind value is like 5 times 10 to the minus 4 for helium-3 to 4. So it's not even going to show up in this kind of histogram. Even though this is only, say, like 10%-ish helium-3, that's a huge increase over the solar wind values. So somewhere you're having flare material that is populating for so these are 4 different events, and you can see the ratio is all over the place. So we get a lot of variation in terms of the composition. So this is, I think I've said this word 17 times, but I'm going to say it another 17 times, is there's huge variation. I really liked the statement of suns are like cats, I think is what you use. I want to say the SEPs are like cats because everyone is different and everyone's very particular about what they're doing. So not only do they vary dramatically in terms of the intensities and their spectral indices, you know, their spectral shape, but also their composition. And so all of this stuff is giving us clues about how they originated and how they got to us. And so we have this wealth of information. And of course, if fundamentally we want to understand two basic things, right? So you've got to accelerate the particles somewhere, got to have an acceleration process, and then you've got to get them from wherever they were accelerated to where you observe them. So that's transport. So at the surface of things, it seems pretty straightforward, right? You've got just two different things. You got to understand these, boom, you'll understand every SEP event that comes along. For those of you who have cats at home, you understand the analogy in about 10 minutes. Okay, so basic acceleration processes. We have two basic acceleration processes, which we think we understand pretty well. The first is shock acceleration. You drive a shock through a solar wind or whatever, you've got turbulence, it's banging particles, you know, particles are scattering off the turbulence ahead and behind, and as they cross back and forth and this whole thing moves out, they gain energy until eventually the shock can't hold it in that space anymore. Reconnection, this was talked about before, you get these canceling magnetic field lines, and then you get turbulence, and then that can accelerate particles as well. So it seems like two processes, not too many processes to handle, we kind of understand that. Transport, these are charged particles, they're in a magnetized plasma. How hard can that be? That's like E&M 101 or something, right? Okay, as always, and you can see all the empty space here, and you know where I'm going with this. The devil's in the details. I know that's an overused phrase, but it's absolutely true. Acceleration. The acceleration, what you get out of the acceleration, how efficient it is, really depends on the conditions in which it happens. Depends on the strength of the shock, depends on the turbulence around the shock. It depends on the density of the material around the shock. Also, the question is, what is being accelerated? As I just said before, it's like if you're accelerating stuff out of the solar wind, you might expect somewhat solar wind type composition. Spoiler alert, that's actually not what you get because of these conditions. You get preferential acceleration of certain things. But in particular, if you have flare material, flare accelerated particles that were put out before the shock went by, and you've got helium-3, now you can be accelerating that helium-3 up to high energies as well, so you can get other stuff that's in there. And then, of course, the question is, how do you escape from that acceleration region? We understand shock acceleration. Basically, the particles get to too high energies, their rigidities are high enough that they're no longer scattering off of the turbulence around, and the shock is not strong enough to kind of keep it in that range. But in terms of flare acceleration, a lot of times that acceleration, reconnection, is happening on closed loops. Things are bouncing back and forth. And the question is, how do you open those loops? You know, we wave our hands and say reconnection suddenly opens this loops and everything flows out. But in reality, it doesn't really work that way, and it's not very simple. And then, of course, transport. Well, okay, these particles don't just gyrate around the magnetic field lines and come directly to you. They're scattering off of all kinds of turbulence that is in the interplanetary medium. And the solar wind conditions. Solar wind, as I mentioned before, it is not constant. It is, there's fast solar wind, there's slow solar wind, there's structures in the solar wind, and all of those things, including a coronal mass ejection itself, which is this big magnetic obstacle, can distort where these field lines are going, which means that the particles are being distorted around, and they can sort of scatter back and forth. They can cross field lines, which they're not supposed to do, but we call it cross field diffusion. They kind of move around, and we see particles all over the places, including at high latitudes that you wouldn't expect to see them. So we have evidence that this is also a very non-simple situation. And of course, we have observations. We have the observations of the flares and the CMEs and the radio bursts, and that tells us a lot about the conditions and stuff that's going on in acceleration. We have observations of the solar wind and the CMEs in situ and the SEPs. So you would think we have all these pieces, and we should be able to put it all together and make it make sense. Well, so this is sort of how it goes, right? You have these active regions on the sun. If they're strong enough and they are active enough and they do all kinds of flux cancellation, you can get a flare that erupts that maybe you see either with our imagers, or you see in X-ray data from, say, GOES, and that might create an SEP event. But it turns out Sometimes it doesn't. And then, if you are lucky, you can also have a flare that creates a coronal mass ejection that goes out, and that coronal mass ejection might drive a shock, and that shock might also create SEP events. But sometimes it doesn't. So the problem is that a lot of times we're looking at this, and this is what the Space Weather Prediction Center is struggling with all the time, is they're trying to take this and predict whether you're going to get this, whether you're going to get this, or whether you're going to get this, and tell you like 3 days ahead of time. And if anybody knows how well prediction of whether it's going to rain or not is in New England, you can guess at how good this is. So this is really difficult, and so we try to understand all the processes that are happening in all these different arrows to try and figure out what is going to happen, whether we're going to have an event or not, and also what kind of event is it going to be. Is it going to be helium-3 rich? Is it going to have a lot of iron? Is it going to have big intensities, big spectra, so forth and so on. So we make these beautiful, NASA loves their fleet chart and everything, but it's really deceiving. It looks like we have lots of data, but the reality is there's a lot of, this is not to scale. I'm sure this is a surprise to you, right? There's a lot of space in space. And I like to make the analogy that, and this is particularly apt here, is that that fleet chart is if I've gone down to the beach here at Long Beach, and I'm sitting here on the thing, and I'm looking at Hawaii with my binoculars, and I'm looking at some storm in Hawaii, and then trying to relate that to the waves that are coming up and knocking on my feet as I'm standing in the sand. And there's a lot of stuff that's going on in the middle. And then, never mind, we're only looking at one side of the sun. If I'm in the Solomon Islands or something over there, I'm seeing a completely different sun than I am if I'm standing here at Long Beach. And we don't have spacecraft generally in the Solomon Islands, or the equivalent anyway. So the question is, what's going on the side of the sun that we're not looking at? And so this what used to be, for a long time, and unfortunately kind of now, is sort of our view. So this is the sun sort of unwrapped, if you will. And this is, the center here is the sun-Earth line. And we can see about 60 degrees on either side. We can kind of get this view of what's going on. You can see the active regions and so forth. And the problem is you have these dark spots that we really couldn't see what was going on. And a lot of stuff changes as it goes around and comes back the other side. So there was this great mission, still is a mission, but it was called the Stereo. It was 2 spacecraft. It was launched in 2006. And it had Stereo A, stereo ahead, Stereo B, which is behind. And basically they're in slightly different orbits from the Earth. So one actually drifted ahead of the Earth, one drifted behind the Earth. And by the time we got to about 20, and you can see here there's the time markings, when you get to 2011, we suddenly have a full 360-degree view of the sun. And now we can see the active regions that are on the back side that are going to come around to bite us on the front side, potentially. The only problem with this, of course, is that it was impossible to stop the spacecraft there. They kept drifting. And so they drifted around, and then they hit the backside, and then they started coming back forward. The other problem was we actually lost Stereo B right around here. So that spacecraft, we were testing it in a maneuver, and then it basically just stopped responding, and it went on its merry way. And so now we have not quite stereo, we have more of a mono, but still we have all these spacecraft, oops, let me get back here. We have all these spacecraft at Earth, so even with one stereo, you can get multiple views, and it's great. The problem is, of course, is it didn't stop, and it's now basically right next to Earth. It will continue to drift around, but it takes about 17 years to go all the way around. So, we're kind of biding our time as Stereo A, sits here. It's going to eventually drift around. Hopefully it keeps working. But right now, we're kind of stuck back in this sort of singular view of what's going on the front side of the sun. So one thing that's actually helping a lot with that, if we go to this chart, is, of course, Parker Solar Probe, which was a spacecraft that we launched, and it's basically moving to be really, really close to the sun. It's in this crazy orbit, which is taking it through swingbys of Venus, getting closer and closer, so its perihelion is getting very close to the sun. And this is the current orbit that it's in right now, and it's getting down to, I think it's about 11 solar radii. So that's now in solar radii. There's 200 solar radii roughly between the sun and the Earth. So you can imagine it's getting really, really close. And it's seeing a lot of really interesting things. And of course we have solar energetic particle instruments on there, which is what we spend a lot of time looking at. The problem is, of course, when you're looking at them as you're zipping through this region, they look really different than they are when you're just sitting over here and watching them wash over you. So we're trying to understand that as well. So it's kind of complicated. There's another sort of instrument, spacecraft that was launched fairly recently, which is called Solar Orbiter. It is also going close to the sun. Not quite as close. It's going to 0.3 or so AU, about 66 solar radii. But eventually it will go out of the ecliptic plane in about another few years. And so we'll finally get some images sort of not right over the pole of the sun, but kind of, at least at a significant incline. I think it's going to about 27 or so degrees. And so we'll get some really nice images. And it has imaging instruments as well as particle instruments on it as well. Okay, so this is the space age. As we talked about, solar event, SEP events occur with the solar cycle. Everything, as we heard, it's all governed by the magnetic field. As the magnetic field goes up and down, we get activity in terms of sunspot number. We also get all these spikes are SEP events. And you can also see the GCRs vary in opposition to those. But this is the space age. This is the time period that we have all these great measurements, right? And you can see the sun's been going on for a long time. And this is the chart that Julian showed, but this is actually the record that we have of actual numbers of sunspots going back to 1750 or something like that. And you can see that all these different cycles are not the same. They change a lot. In particular, the last couple of cycles don't really seem to be like the biggest ones we have. So the question is, the stuff that we're observing now, is that actually representative of what you would have seen before? And so there are some ways that we can look at it. It turns out that these big events, anytime you get a big event like this, we often call them ground level enhancement events, because they interact, the protons will interact with the atmosphere, as we heard, and it will create a whole bunch of things, including cosmogenic isotopes. And in particular, we're talking carbon-14, beryllium-10, chlorine-36. You've got to stay seated. You asked me to talk about this part, so I'm going to talk about this. Anyway, so basically you can see these. I only have a couple more slides. You can see these in the ice cores. You can also see it in tree rings. They respond slightly differently. Tree rings is basically carbon-14, ice cores is the other guys. And you can use the carbon-14 to reconstruct a longer history of the solar cycle, which has been done here. You can see going back to like 950 or something. And you can see these bigger variations if you average this over larger things. You can see things like the Maunder minimum and the Dalton minimum and all those guys. And so there's some indication that this reconstruction works. But the question is, do you see the effects from SEPs? And the answer is yes, if they're big enough. The problem is that you have this GCRs also create these cosmogenic isotopes, and they change with the solar cycle. So you have to have something that's big enough that is going to overwhelm the GCRs, and not just for a short time period, because the ice cores and the tree rings are basically an annual measurement. You can't get much better than annual. And so it's got to, and these SEP events happen for a couple of days. If you have a series of them, maybe 10, 2 weeks or something out of a whole year. And so it's got to be big enough to overwhelm all the GCR stuff that you get over years. And there have been a few events, 5 extreme events that have been verified by you, both the tree rings and the ice cores, and then 3 other possibilities that look like they might also be big events. But we've only looked at about 16.5% of the data. Now the problem is, of course, we didn't pick those data at random. They're very specific time periods where people thought there would be something good there, so you can't just extrapolate from that 16.5 and say, well, huge events happen this often. But they have taken those data and they've tried to sort of come up with an idea of what the spectral shape looks like. And you can see these are the events, these are some of the events I showed on the previous view graph, and you can see that these are orders of magnitude bigger than anything we've seen in space, or since the space age. And so what their characteristics are like, or whether they're going to be anything like what we've already seen, is a little hard to tell. I will point out, I thought this was interesting, that no current events have cosmogenic isotope signatures, so we can't actually test this. We don't have anything strong enough that created a signal we can see. Even the Carrington event also didn't create a signature that we can reliably identify. So, and that was the big spectacular event, right? And so, that we have measurements for. There are associations between big SEP events and big Aurora events, so you could try and extrapolate and use very old records from Aurora, but there's not a nice one-to-one thing there, so it's really hard to evaluate that. I just thought these were really cool. This is in a Soken paper. This is a illustration of a big Aurora event in 1582. This is a Babylonian inscription describing an Aurora event in 567 BCE. But that's kind of the information we have, is like, there was a huge Aurora event. I don't know anything about the SEPs, but maybe that helps. I don't know. All right, so this have a lot of data. Basically, they're all cats, so there's no typical one. It's very hard to define that. It's very hard for us to back up from all the details and get the nice overview. Connecting the remote sensing and the in situ stuff is really hard because there's a lot of spot stuff that we're not monitoring and everything is changing all the time. And the space age stuff we have may not even be typical for extreme things. We don't know what the limit is, and we don't know what governs the limit of what we can possibly see. Am I close? Close. Okay.